Well, hello, and welcome to the Graduate School of Biological Sciences at Mount Sinai. I'm John Morrison, Dean of Basic Sciences and the Graduate School, and I'm in San Diego rather than there with you because orientation always seems to be at the same week as our family vacation in San Diego. But with the help of Jose, I've taped something for you. Last year, I taped 10 things I learned in graduate school, and that's available on the website. So I didn't want to do that again. So what I thought I would do is go through, with the help of my notebooks, my lab notebooks, which I still have from the 70s, I'll give you some recollections of building a dissertation with my thesis advisor, Dr. Mark Molliver at Hopkins. And I could never have done this without my lab notebook. And you'll see there's some important lessons here, but also we'll try and keep this a little light. Okay, so here's me. 1974, weekend I graduated from Hopkins, undergraduate. It's my parents, one of my brothers on the left there. And you may not appreciate this, but I did get a haircut for the occasion, and I believe that's a clean t-shirt I have on there. So I started right off by making about 3 or 4 mistakes. First of all, I stayed at the same institution for my Ph.D. At Hopkins, which many people think is a mistake. In the end, it turned out not to be a mistake at all. But I entered a Ph.D. program in neurochemistry that fall at the School of Hygiene and Public Health. So I decided that isn't what I wanted to do because you start off by grinding up the brain to figure out what neurotransmitters are involved in a given brain region. I didn't like that. I wanted to put the neurotransmitters together with the circuit. I couldn't do that at the School of Hygiene. I didn't have a lab like that, and so I had also the wrong mentor. So wrong area of science, wrong place, wrong mentor. But I quickly adjusted with the help of Dr. Mountcastle, a very eminent neuroscientist at Hopkins at that time. I looked at several programs, decided the best thing to do was to switch to the School of Medicine, Department of Cell Biology and Anatomy, and work with a neuroanatomist there, Dr. Mark Molliver. And as you'll see, turned out to be very successful. So I recovered, didn't let that mistake slow me down too much. Now, just a little background on my thesis project. The conceptual goal of everything we were doing was to reframe neural circuits in the cerebral cortex according to the neurotransmitter used by that circuit. In those days, we weren't thinking about circuitry in the context of neurotransmitters. It was just starting to happen. And our target circuits were the monoamine projections from the brainstem to the cortex that had just been discovered, particularly the norepinephrine and serotonin-containing projections. There was a tremendous amount of interest in these projections at that time because we knew that many drugs to treat particularly psychiatric disorders function through these systems. But we had a major technical hurdle. You have to be able to see the circuit in the microscope to analyze it. And it was very difficult to see these circuits at that time with the available technology. So, Dr. Molliver's initial stab at the design of a thesis project was, hey John, Joe and Reinhardt have an antibody. And it was just about that. Joe is Joe Coyle, and Reinhardt was Reinhard Jana, his postdoc. And they had an antibody, as you'll see, to dopamine beta hydroxylase. So we launched an effort to use immunohistochemistry to visualize these circuits and then be able to analyze them in detail. It took us a while to get there, as you'll see, but essentially nobody was doing immunohistochemistry in the brain at the time. Now here's a page from my lab notebook. You can see it's June 15th, 1976. I took these very detailed notes of every meeting with Dr. Molliver. These meetings would go on for 2-3 hours. And here you have all of these various manipulations we were trying to do to turn the norepinephrine into a fluorescent molecule and visualize the circuit that way. Very problematic. At the very end of the meeting, Mark mentions Coyle's immunochemical methods and a possible experiment. And this is June 15th. First time we really talked about the use of this antibody. July 14th, we do our first immunofluorescent experiments, animal IF1, immunofluorescence 1, with the Jana-Coyle antibody to dopamine beta hydroxylase that we refer to as DBH. And why that protein? Because that's the synthetic protein, the last enzyme in the synthetic pathway for norepinephrine. So If DBH is present, norepinephrine is present, that circuit uses norepinephrine as its neurotransmitter. Now you can see here our very first experiment. We were missing some equipment. We were missing jars and scissors. So we had to make sure we had that for the next experiment. And these experiments went on, this is July 14th, next is August 10th. Now, detailed notes on that day's experiments. And what you see here is, it says here, the sections have had something wrong with them. The globular effect on top of the reaction has been bad. And it goes on to describe the fact that we can't see anything because some precipitate has occurred on the section. Now, the technical term for the globular stuff became bullshit. Now, how did that become the technical term? Well, I was working with Reinhard Jana. He was German. His English wasn't that good at the time. And at the end of each day, the experiment would run until about 10 o'clock. I'd sit down at the scope. He'd sit down next to me. And day after day, he would hear me say, "Oh no, the bullshit's there again." So he came to use the term bullshit in an almost technical fashion. He would sit down and he'd go, "Is the bullshit there? Is the bullshit there?" As if to say, "Is the precipitate there?" So that's what we named it, although we didn't call it that in any of the papers. Now, this is September 16th already. It turns out that this very detailed outline you see here for a paper on neocortex was overly optimistic. Why was it overly optimistic? Because the globular stuff is still there. So the bullshit remains. So the bullshit remained until Mark came up with a great idea. Now you see this is IF 16 and 17, so this is now 17 animals in, and we had to make all of our own antibodies and everything too, so it took a while to analyze an animal. This is September 24th, and Mark suggested perfusing the animals. Now nobody did that for immunohistochemistry in the brain until we tried it, because everybody assumed that if you used any aldehydes, you would destroy the antigenicity of the protein and the antibody wouldn't work. But we used very light fixation, 2% paraformaldehyde. It was beautiful. It perfused through the heart. Perfusate goes to the brain. The fibers were beautiful, no globular stuff, and we saw a far more rich innervation of the cortex with these noradrenergic fibers than had ever been appreciated before. And we also were able to start to see how they were organized in the cortex. So, the first paper, Reinhardt was the first author, describing this use of this antibody and this approach, and it says right in the abstract, this method applied to paraformaldehyde perfused tissue consistently yields highly sensitive and selective staining with excellent cytologic preservation. Turned out that was probably the most important part of the paper, because from that point on everybody perfused when they were using immunohistochemistry. Also, your papers got accepted a lot faster in those days. You can see we sent this in on Christmas Eve, and by January 4th it was accepted. Wish it was still like that. Now we have a real outline for a cortex paper, and you see IF, that's immunofluorescence, right up top. Various cortical regions. We're going to do a laminar analysis in all of them, layers for all. And then we're going to discuss the location of the terminals as well as the route to and within cortex. So, we're on our way now. So then, I enter a different phase of my thesis work, learning to write according to the rules of Mark Molliver. Well, whenever you wrote a paper with Mark, which was very, very painful, because he was unbelievably obsessive about it, at least several times during the process of writing that paper, you went to his house for dinner. It was always a great dinner, great wine. About 10 or 11 o'clock, Mark would say, "Would you like a glass of port?" And that meant that he was starting to think about writing. So you drank the port about 11, you start writing about midnight, and write all night. And that's how our papers were written. This one took, I think 18 months is an exaggeration, but not by much. Multiple of these all-nighters with port, and many concessions on use of the word "the." That was one of Mark's things, whether or not you used the word "the" in this case or not. Long discussions. But, very nice paper. And you can see here this crazy diagram that looks like a bunch of eels swimming around. And this is meant to show the orientation of the noradrenergic fibers in each layer. And This shows that they're actually innervating these deep layers, which wasn't appreciated until we did this. Everybody thought all the fibers were only up here in layer 1. Also shows these fibers running rostrocaudally through the cortex, which will turn out to be quite important, actually. Nice little wedge that come. I like that effect there. Yeah, not quite an illustrator image, but. So then we started analyzing the trajectory of this system. It originates in the brainstem, innervates the entire neocortex. How does it get there? What would damage at various levels of the neuraxis due to this system? So we first lesion the dorsal noradrenergic bundle. I'll show you where that is in a second. So these are numbers 1 and 2 of well over 100 lesioned animals that went into this analysis over the course of my thesis. And what I want to point out to you here, I think this is an important lesson, is the careful post-surgical observations and the veterinary care that I offer these animals. First of all, the DNB1, his eyes are open. DNB2 he's really not doing very well. His eyes are closed. This animal doesn't seem to be eating or drinking, and it's somewhat aggressive. It says right there, somewhat aggressive, and I know that because he bit me. This guy sits with his head in the corner. So what did I do? Well, I gave them both a Clark bar, but I don't think they made it anyway. So we had to start over. Now here we see serious design of the thesis. Another meeting with Molliver, and this is April 11th, 1978. And we see here, you can see the word thesis. So you know I'm designing my thesis here. And you can see all these different lesions on the left side that we're going to do. Different kinds of cuts in the cortex, midbrain lesions, anterograde studies, retrograde studies, different kinds of lesions. And this diagram turns out to be very important. This was our hypothesis that if you did a lesion a cut in the coronal plane, you would disrupt all those fibers running in the deep layers, and therefore you would denervate the rest of the cortex. Whereas if you had a cut in the sagittal plane, since the fibers are running this way, you wouldn't have much effect on the innervation of the cortex. And this was important because this started to explain some of the behavioral and functional effects of different kinds of lesions that occur. So there you got it. There you see, it's very, again, it's not quite what we would do now with Illustrator, but there it is. So a little more design. Here you see every A, B, C, it's a separate, A and B over here. You see this is lesion of the dorsal noradrenergic bundle, medial forebrain bundle, septal area, and all these lesions were designed to either completely knock out the circuit or knock out parts of the circuit. And these are these knife cuts that we used in the sagittal plane versus the coronal plane. We also removed a large part of the frontal pole because our hypothesis was these fibers were coming up through the frontal pole, which is not what had been proposed before. And that meant that if you had frontal lobe damage, you would knock out the noradrenergic, and for that matter, serotonergic innervation of the entire hemisphere. And that would start to explain a lot of the effects that you see in humans from stroke and frontal lobe damage. But this is a rat model, remember. So then we did all these experiments, like I said, at least 100 different lesions. And here you can see all the different lesions, 9 different lesions, the method that we used. And see, I learned to write much more succinctly than Mark. I have all this on 2 pages. And Abby, my wife, who was my girlfriend at the time, knew how to type. So she put this in a nice format. I didn't know how to type. And then you have here 4 quite succinct summary statements that describe the entire intracortical trajectory of this system. So very nice. So this, along with the paper that had already been published with the eels floating around, ends up my thesis. And Abby's a really good typist, so she typed my whole thesis, which I defended in April of 1979. We didn't have word processing. We didn't work on computers at all. So every time you edited it, and Mark edited it a lot, Abby had to retype it. So you don't want to go back there. But there it is, front page of my dissertation. More writing lessons from Mark, but this one generated a science paper. Why a science paper? Because we finally had described how this system innervates the cortex, and it really was very, very different from every other projection to the cortex. And we demonstrated these very widespread effects of local cortical lesions, which had implications for humans and for frontal lobe damage. So there we have it. This diagram, again, not quite as sophisticated as what you would see now, but became actually very widely used. And this was the sort of guts of my thesis right here. Now, a paper that was published after I finished was a much more detailed. This was the one with all the lesions. And we took to calling this a tangentially organized cortical afferent. Well, what does that mean? Well, it's organized tangential to the cortical surface, sweeping through the cortex. And that's not the way cortical afferents were supposed to be organized. They were supposed to be organized the way the thalamic projection is organized, point to point, nucleus to region. And so this was actually quite unique and was perfect for a system that could modulate activity throughout the entire neocortex. But this was all in the rat. And the rat is a smooth cortex. It's called a lissencephalic brain. We wondered how this would work in a brain that had sulci and gyri. I mean, it seems that it might be much more difficult for the system to be organized that way. So this is a letter I wrote to Floyd Bloom, where I ended up doing my postdoc in June of 1979, right after I defended. So I did a short postdoc with Mark. And he's saying here, in addition, we are presently investigating the intracortical trajectory of the ceruleocortical projection in a gyrencephalic brain. Okay. Well, you would normally, I say what a stretch that was, you would normally do that in the monkey, but we couldn't afford monkeys. So Barry, another graduate student in the lab, got a pig. So this led to the famous pig, I guess I should say infamous pig experiment, where we did a frontal lobe removal in the pig, and 2 weeks later followed with an intracardiac perfusion. Well, we'd been working on rats. You know, pigs are big. Even this pig was big, about 100 pounds, I'd say. And we really didn't anticipate the difficulty that would come from just the size of the heart. So you can see, now it's easy to tell who's the graduate student here. He's the one that's all messed up. That's me. Mark was out of the way of the heart when we started the intracardiac perfusion. But you can see how attentive and helpful he is there. And there we are, working side by side. A little bit messy, but it worked. The perfusion proved difficult but successful. The rodent findings held up in the gyrencephalic brain. We published an abstract. That was Barry Kosofsky was first author, with an N of 1, because we couldn't imagine doing another pig. And Morrison, me, gladly moved on to more refined experiments on monkeys at the Salk Institute. So that brings us to the end of my time at Hopkins. 30 years later, I've had many students of my own, and I oversee the Ph.D. and M.D. Ph.D. programs here. And I've concluded the following. By the way, I was Mark Molliver's first Ph.D. student, and he's an M.D., not an M.D. Ph.D., so he had never gone through this experience himself. But he got it right. How did he get it right? Well, he had the perfect balance of guiding me intellectually by giving me independence. So I always felt that he was right in the middle of this process, helping enormously, but I also felt the level of independence that a student wants to feel with their thesis project. He also taught me very early on the power of collaboration. Remember, one of the first comments I make here is Joe and Reinhardt have an antibody. So that launched a very, very powerful collaboration that continued for many years. And they had an antibody. We didn't know how to make antibodies. We had neuroanatomic and microscopic expertise. We put the two labs together, and it worked. And I think that's a very important thing for you to important lesson for you to keep in mind. The importance of determination, discipline, and rigor. It helps to be smart, but you know, you can be brilliant and still not succeed in science without these three elements. That June through November, December, whatever it was, where we were trying to get this method to work, it was tremendously frustrating. It was experiment after experiment that just didn't work. You know, the bullshit remained. But we kept going, and it finally worked, and it was very successful. And maybe most importantly, Mark taught me that it's supposed to be fun. He was a very serious guy, but we had a lot of fun in that lab. We had a lot of fun in graduate school, and it really is supposed to be fun. There are a lot easier ways to make a living than being a scientist, so make sure it's fun. So my advice to you, take some risks, Choose your mentor carefully. Ask an important question. Don't give up, and enjoy the process. Thank you, and I'm going to go to the beach. Have a good week.